Hello, in this video we're going to create a Serpenski's triangle in R. Now this Serpenski triangle is actually one continuous line and it plots it into this Serpenski triangle. Now this is actually inspired by a Numberphile video just recently where he had Matt Henderson on here and he was illustrating drawing these Serpenski triangles in Mathematica. And I wondered if we could do it in R. And so that's what this whole video is about. So, as I mentioned, this is from Numberphile's video. And here's the link to that video. And I always copy and paste my code into the comments if you want to use this code. So, if you haven't watched it, I'm going to explain what they do in this first function here. So first of all, I like to clear everything out. And the Serpenski path tells us to go forward 1 unit, turn right or left, go forward 1 unit, turn right or left. And that's what we're doing. And so we start out with a path of x. That means go forward 1 unit. And in my case, it means go up. So from the point 0, 0 to the point 0, 1, go up. Now to grow this, whenever there's an x in our path, to go one more depth, and I'll make it more in a second, whenever you see an x, we put in this sequence, y, x, y. And this says go 1 unit forward, turn right 60 degrees, go 1 unit forward, turn right 60 degrees, go 1 unit forward. And the dot G means grow. We're going to, whenever there's an x, we're going to grow it with this pattern. Okay, silly notation, but that's what I used. Then the next, so that's the depth of 1. Depth of 2 is 2 iterations, and we're at this. So, but whenever we see a y, we're going to grow the y's with this sequence, and we're going to grow the x's with this sequence, and grow the y's again with this sequence. And then we just keep repeating that process until we want to stop. And to do that, and this is absolutely not an efficient way to do it in R, and I thought about trying to vectorize this process, but I'm like, this works and it's kind of cool to show. So first of all, we need to know how long our path is, and I call it ruler. I want to measure how long it is, and depth is how many times we want to iterate this. And that's really this function. And so we substitute in, and then depending upon the depth we want to go, we reset our variables, and then we print out path. And so let's look at a depth of 1, so a Serpenski path of 1. And then I also print out how many characters are in it. This is 5. Remember, we replaced the x with this pattern, y plus x plus y. Now let's go to a depth of 2, and notice that this y we replaced with x minus y minus x. And then that plus comes down, and then this x here we replaced with the grow x component, y plus x plus y. Then this x comes down, and then this y, the next y, we replace with y minus, or x minus y minus x. And there's 17 characters. And then, so if we want to go a depth of 3, then we're going to replace each of these x's and y's with that respective, pattern, depending upon what you have. And then it's this. And so each of these x's and y's have been replaced with their respective patterns. And then a depth of 4, we replace each of those sequences of x and y's with this, the new pattern, and then it just grows and grows. I'm going to not print them out each time because it grows pretty fast. So here there's 485 characters. If we go a depth of 5, a 6, there's 1,457. Here's 7, 8. But notice there was a pause there. When I do 9, there's even a more pause. So it's like a 3 or 4 second pause there, growing that path. So that's the process, and that function that we did is actually the first part of plotting this Serpenski triangle. So this is the function that is exciting here, the Serpenski function. And the first part of it is literally growing the path to the right depth. So we create this character string of functions. Well, to us they're functions. It's x's and y's and pluses and minuses. And then we have to take those and convert them to xy coordinates. So we create x and y variables, of the right length. Angle is 0. Now that's a little weird because we're going straight up, which a lot of times my mind thinks of that as a 90-degree path. But the way he did it on the piece of paper, the brown paper and Numberphiles, he went up. And then later in Mathematica, he went to the right, initially, an angle of 0. And I'll show you how that affects the Serpenski triangle as, when we get to plotting each of these. But I followed the brown piece of paper. So we take those, and then here we start growing the x's and y's. So we put in the right coordinates depending upon the path that we take. Notice we're looping over the path, and then if it's an x or a y, then we know where to go. Then we plot it, and we go from there. So let's look at Serpenski triangle, a depth of 1. So I have to minimize this. So this is it. So remember, a depth of 1s, we start out with an x, and then we go one iteration, and we get an x plus y plus x. So x means go forward 1 unit, plus means turn right 60 degrees, go 1 unit. And notice that here, we didn't quite make it to 1, right? If we went perpendicular to this, we would go 1 unit and we'd be at a 1, but since we're diagonal, it's a little bit less than 1. Then it says turn right 60 degrees and go 1 unit. That's what we do here. Now let's go a depth of 2. And so remember, we start out at 0, 0. We go forward, and then here's a left, a right, and we go 1 unit each time. Here is a depth of 3, Serpenski triangle, and it's starting to sort of look triangle-ish. Here's a 4, and notice, look at that line. It's all one continuous line. That is so cool. So there's a depth of 5, depth of 6, depth of 7. Here's an 8. Now when I do 9, it's going to take about 4 to 5 seconds to do a depth of 9. And there it is. Now I'm going to do a depth of 10, but that takes 40 seconds. But I'm going to explain how using the brown paper approach, where you go up 1 unit first, as opposed to in Mathematica, his program, you go to the right 1 unit first. So here we start at 0, 0, and we go up 1 unit, and it creates, I'm going to call these sideways triangles that point left or point right. If we, instead of going up, we go right, this triangle is rotated 90 degrees. So these triangles would point up and point down depending upon, the depth that you want to go to traverse these. And here it is. So here's a depth of 10, and that's it. And again, I would encourage you to watch the Numberphile program where Matt Henderson talks about this and using Mathematica, and it's actually quite fascinating. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.